Okay, I'm going to talk now about Newton's second law in the rotation world. And I've got a pulley here, and it's mounted. It's got some axis that it's rotating around. If I did a free body diagram for that, by the way, it would look like this. It would look like mg and some support force or normal force. Okay? The reason I'm writing this is these usually don't come in pulley equations. We don't usually worry about those when we're talking about the rotational stuff because they go right through the center of the pulley. So they don't have any torque. They don't make the thing rotate. But don't forget about them. Don't forget about mg and whatever that support force is. Okay? It's just useful to understand that those are still forces acting on the pulley. They're just not rotational forces. So Newton's second law, we want to talk about Newton's first law, sum of forces equals ma. Okay? And that I think of that as linear or translational. So if you apply a net force in one direction and the object has a mass, it will move, its center of mass will move in that direction with that, I shouldn't say that, will accelerate in that direction. Depends on what direction the velocity is, whether it moves in that direction. So we know that, but now Newton's second law, if we think of rotational, instead of talking about force, we'll talk about torque. And instead of mass, which is inertia, talk about the rotational inertia, how hard it is to change the object's rotational motion. And if you haven't looked at that to understand what that has to do with, what it has to do with the mass of the object, and it has to do with the distribution of the mass in the object. Okay, the farther away most of the mass is, the more rotational inertia there is. And instead of A, we talk about alpha. So in a really simple application, let me say that I pull with a constant force F, okay? And in fact, since I've got some numbers here, I'm just going to say 10 newtons. And I want to find the angular acceleration of that pulley. So I've got some string wrapped around it. Well, if we look at this is something that confuses some folks. They're like, okay, well, what's the angle for the torque? Let's draw this up. Sum of torques equals I alpha. Well, there is only the one torque, only the one force. Once again, we have mg down, we have normal force up. This is the one force that causes a torque. And if you think of it, the perpendicular distance is just the radius of the circle. So we end up with the torques. This is the only torque. And I'm going to call this direction positive. Now, the convention is generally counterclockwise positive, but I'm overriding that just so I don't have any weird negative signs going on, okay? So R times the F times the sine of the angle in between, sine of 90, which is just 1, is going to equal I, and the rotational inertia for a pulley or a disc or a cylinder. Let me draw it like this. If you think of it, there's a cylinder around this center axis. Well, a pulley is just a really shallow cylinder. We could also call it a rod, or circular rod around that cylinder. When you're rotating something like that in this direction, and again, the pulley, just think of this being the pulley right there. It's a small, short cylinder. The rotational inertia is just 1/2 mr squared. We sometimes write it as just mr squared over 2 for a pulley, disc, or cylinder. Solid, okay? If there's a hole in the middle, we've got some issues. But certainly for AP1, this kind of thing would be given. So R is 0.5, F is 10, equals I, 1/2 times 1 times 0.5 squared times alpha. So when we solve this, this ends up being 5 equals 0.125. This is 0.25, half of that, times alpha. And this ends up being 40 radians per second squared is alpha. Okay, now be really careful. Make sure that you understand this is the angular acceleration. Get the units right. We could find the linear acceleration of the string, if I'm pulling with a string, by just A equals R times alpha. A equals R alpha. Okay, so we can relate the linear stuff to the angular stuff. If I knew how far something on here was, if we knew its linear characteristics and we could find A, then we could find alpha. And if we had alpha and I, we could find the net torque. We could find out what that force is. Okay, so that's a fairly straightforward thing where it's just, we've got this one torque, the force is given.